All right, so in this problem, we have a roller coaster, and the mass of the roller coaster is 500 kilograms. So let's write that down. And the path, let's see. So B is only up and down motion as seen by the raters with no motion to the left or right. Wait, the path, let me stop and read this. Okay, so I'm taking that second line to mean that it's just not moving in and out of the page. But it's kind of a weird line. I'm not sure if I'm just missing something, but I mean, obviously the cart goes to the left and right. So I'm just going to proceed as if that wasn't there, and hopefully I don't run into any issues. So we know that the speed at A is 20 meters per second. So I'll go ahead and write that down. And we want to get the force exerted by the track. And so let's do a free body diagram of the car at the bottom of the track. So we have the weight down, and we have a normal force up. And I drew the normal force up because I know the net force needs to be towards the center of the circle. So we want to do sum of the forces is MA. So sum of the forces is MA, and then we know A is equal to V squared over R. So I'll just write it like that, B squared over R, and the sum of the forces is normal minus weight, and then I know that this is positive because it's moving towards the center of this circle. So it's MV squared over R. And then our goal is to get I'm calling it a normal force. The normal force is the force exerted by the track on the car. So that's just the weight plus MV squared over R. And then, so we have M, the weight's mg, so we have g here plus v squared over r. And this is the velocity at A. So I'm going to evaluate this for VA. So now I'm going to just plug everything into a calculator. So we're going to do 500 times G 9.81 plus V squared, 20 squared, and we want to divide it by R1. Oh, do they give us R1? They do. 10. So we want to divide by 10. So that I get 2.49 times 10 to the 2.49 times 10 to the 4 newtons. And double check all my math. 9.81 v squared over r1. Great. And we want to get the next for B, we want to get the maximum speed at B, and still we want it to still remain on the track. So at B, it looks like it's at the top of this hill. So let's draw a free body diagram for what's going on at B. So we still have the weight down, and we have a normal force up. Oh, this is interesting, actually. And so we have a normal force up, and we want it to remain on the tracks. And so we need it to still have an acceleration in this direction. So we need the weight to be bigger than the normal force, basically for the net force to be in this direction, right? For the net force to be towards the center of the circle. Sorry, this is just a little unintuitive to me. I think I know that this is the approach that you want to use, but it seems like you could just crank the speed up and make the tracks just arbitrarily strong, but I'll think about that. But for now, I'm just going to say that we need the normal to equal the weight. Otherwise, the F net isn't towards the center. And so we know that that it's not going to be undergoing that circular motion. And so let's see, we want the speed. Okay. Well, let's write down the equation. So we know that the normal minus the weight is equal to, so the F net has to be down. So that's going to be minus mv squared over r. Okay, this actually does sort of reproduce my intuition, because you can, let's see, you can, like for every v you pick, you can calculate the normal force. Like the normal force is always going to be the weight minus mv squared over r. I guess if you crank up v so much, right, then you get that the normal force would have to point in the negative direction, which again is impossible. So again, I guess we'd want to set the normal force equal to 0. That's kind of, I'm like thinking this makes sense to me, I think mathematically, but not quite like physically, intuitively. But I'm just going to keep going through it as the ideas churn through my mind. So the weight is mg minus mv squared over r. Set it equal to 0, and then we get that v is equal to, solving for v algebraically, it's just the square root of gr. The m's cancel and you bring the r, g to the other side. So let's calculate the square root of g times r, and then of course this r is going to be rb. So I'll go ahead and label that, or r2, sorry, which is 15. Put in all these 2's. So we want the square root of 9.81 times 15. And I get 12.1 meters per second. Yeah, I really only have a limited amount of time to do these problems, so I don't want to like stop and ponder if getting an answer that makes sense within the realm of physics. But I'm curious like what would happen, because I mean, it seems like you could just crank up the normal force to keep it on the track. I mean, just have like the world's best glue. But maybe it'd be something about compromising the circular motion. But that would be interesting to think about and figure out how to solve that.